Hey everybody, welcome back to Adventures in Machine Learning. I'm one of your two hosts, Ben Wilson, and joined by
Michael Burke. Hi everyone.
And today we're going to be continuing our conversation from our last podcast where we were talking about Apache Spark. But this time we're going to talk about the aspects of what does it mean to be using Spark and specifically ML libraries that actually interact with Spark, not just stuff that runs on Spark on the driver node or runs in Pandas UDFs, but actual native Spark applications for machine learning.
Hey folks, this is Charles Max Wood from Top End Devs, and lately I've been working on actually building out Top End Devs. If you're interested, you can go to topenddevs.com/podcast, and you can actually hear a little bit more about my story about why I'm doing what I'm doing with Top End Devs, why I changed it from devchat.tv to Top End Devs. But what I really want to get into is that I have decided that I'm going to build the platform that I always wished I had with devchat.tv. And I renamed it to Top End Devs because I want to give you the resources that are going to help you to build the career that you want, right? So whether you want to be an influencer in tech, whether you want to go and just max out your salary and then go live a lifestyle with your family, your friends, or just traveling the world or whatever, I want to give you the resources that are going to help you do that. We're going to have career and leadership resources in there, and we're going to be giving you content on a regular basis to help you level up and max out your career. So go check it out at topenddevs.com. If you sign up before my birthday, that's December 14th. If you sign up before my birthday, you can get 50% off the lifetime of your subscription. Once again, that's topenddevs.com.
Exactly. So let's say you start off by building some super fancy ETL pipeline. It works great. It's super fast. And all of this is done in Spark. Well, there are two options. If you're going to be training and serving a model, you can switch over to some single node operation like sklearn, stats models, etc. Or you can stay in this distributed framework and work with a Spark library. So Ben, what would you say are the main reasons to stick with Spark libraries versus moving to a single node operation?
It's really two aspects. One is your data volume. And by data volume, I mean not just training data volume, which that's not usually a requirement for most models. You don't typically need a ton of data to train something, but it's more on the consumption side. When you're going to be running inference or predictions and your data volume of things that you need to predict on are going to be ludicrously large, and you're going to be using a framework like Apache Spark to do that prediction, then it makes sense to have something where the complexity of distributing the equation, your model that you're going to be applying to a vector of data, keep it in that same level of complexity abstraction that Spark gives you. It's going to be more performance. It's going to be simpler code. It's going to be easier to troubleshoot, diagnose problems, and it's going to solve one of the biggest concerns that any serious ML practitioner should have, which is complexity. Anything that you're building and push into prod, you're going to have to maintain. The simpler it is with respect to moving pieces, parts, and lines of code that you need to keep track of, the better. So if you're predicting, hundreds of gigabytes of data multiple times a day through a model, Spark ML is kind of designed for that. The other aspect that can be incredibly important for you choosing to use Spark MLlib is the algorithms that are there. There are certain operations that can you do that on other platforms? Sure, but it's not the most optimal way to spend your time trying to get something like that to work. So for instance, I think last time we were talking, we have definitely in the past talked about ALS algorithm, alternating least squares, which is a matrix factorization technique where we're taking the users and items columns from a data frame and basically inverting that matrix and doing a dot product between the user matrix and the item matrix. And we get a filled in data set. Well, when you're using recommendations engines, you typically are dealing with a lot of data. You could be having millions of users. You could be looking at hundreds of thousands, if not millions of products or titles or, whatever it is that you're trying to recommend. And the scale of memory pressure that is present in those algorithms is pretty daunting. So spinning up a single virtual machine that can handle that, or that has that capacity to hold all of that in memory. There's not a lot of them that exist out there. They're usually super expensive to spin up. So Spark is a much cheaper and more reliable way of doing that.
Got it. So more efficient processing on the server/consumption side, and then also support for algorithms. What other algorithms are not in common Python libraries that are in Spark ML or MLlib?
I mean, to be honest, not a lot. It's usually the other way around. So when you're looking through the heavy hitters that people use the most on Spark MLlib, you have stuff like ALS, FP growth, which FP growth, that's market basket analysis. Like, hey, the consumer A purchased these 17 things in their checkout queue or in their order. If consumer B has 3 of those things, what are 5 other things that they're highly likely to buy? And that's another factorization technique that's done. It's just by basically building trees and traversing them. And that's a distributed algorithm, and it can really benefit from that distribution because of the way that it's architected. But if you look at some of the other common algorithms, you have stuff like XGBoost is native on Spark now, part of Spark DL package. You have random forest, gradient boosted trees. You have decision trees, linear regression, logistic regression, generalized linear models. You have support vector machines. There's a neural network implementation in there that I don't think I've ever met anybody who's used multi-layer perceptron classifier on Spark outside of demos or just seeing what would work. Usually people are like, oh, if I'm going to use, this sort of old school deep learning technique, I might as well just use TensorFlow or PyTorch. But it's there. MLPC is kind of a slick algorithm. It's pretty cool to play around with. But a lot of these algorithms that have implementations, you have something like k-means that's in there as well for unsupervised. And you notice that you don't have other companion algorithms to those. So when you look at sklearn, you're like, wow, there's so many linear models that are in here, or there's just dozens of these esoteric models that don't exist in Spark MLlib. And I've had people ask me before, they're like, well, why doesn't Spark implement all of these? And it's like, well, most of these algorithms, when they're implemented in something like scikit-learn or in stats models, they're building those on the shoulders of giants that have come before. So they have a reference code base, usually in R, where a lot of these things were originally implemented. They're looking at how that execution looks like in R, and they're converting it to Python, or they're interfacing directly with BLAS operators if they have to do vectorized math, or they're using the same Fortran library that powers that R implementation. And the Python aspect of it is more of a structural framework API wrapper, but the underlying execution is the same. Spark's a bit different. Spark can't rely on those same exact libraries. It has to use a different distributed vectorized engine in order to do that math. And the one that is used is called Apache Breeze. A lot of the core founders of Databricks who built out stuff like Spark MLlib, they're also part of the team that contributed to Apache Breeze. A number of the people on the meta team that I work on, that's those people. And you look at how that differs from the libraries that sklearn calls, or the Python libraries that are wrapping these low-level operators. They're pretty divergent. So the reason these, all of these esoteric algorithms don't exist in Spark MLlib is because there's just not enough demand for them. And it takes a lot of time and effort to re-implement that from scratch in a distributed system. It's tough. It's really complex. It takes a lot of resources to do it. So people aren't going to volunteer for, I'd love to spend 6 weeks of my life implementing this algorithm and writing all the tests for it and validating it and building demos and writing docs for it, for something that there's maybe 3 humans on the planet that are interested in using it. Like, nobody cares. Just to use the scikit-learn package.
Yeah, you bring up a really good point in that Spark, I think, sort of has a niche use case in that it's, as advertised, is designed for handling tons and tons of data. If you're doing EDA, there's often other libraries that exploratory data analysis. If you're doing that, there are often other libraries that have a lot more infrastructure in terms of model support, documentation, tutorials. The community is just bigger, also because they're older. And then also, they have a lot better visualization and diagnostic tools after training. Stats models is not a great example, but even stats models does have solid diagnostics at the end. In my experience, the gold standard is R. They have such easy usable model outputs. Like just look at dot summary, or I guess in R it's summary. But a lot of the dot summary operations in native Python more standard Python languages like sklearn and things like that tend to be a lot more effective than what is developed currently in PySpark. And do you think that would change?
Interesting. One anecdote to add to that, R borrowed all of that from SAS. So SAS got there first for their like model report and validation and their visualizations. That was all started in the 1980s. And outside of, if we're not talking just about open source, I'd say they're the gold standard with just ML functionality in general. But you have to have Scrooge McDuck money to afford like large scale SaaS deployments. And you need a workforce that's trained up. It's a very powerful suite of tools that once you know how to use it, you're going to be more effective than most people trying to do stuff in open source. You just have to have a massive budget to do it. That's just why there's target audience for that software suite is like Fortune 1000 companies and a lot of traditional engineering firms. But back to your original question, is PySpark going to be going down the path of getting better reporting for models? Yes and no. The most unanswered answer there is MLlib isn't going to natively have more stuff put into it to support this aspect. So it's not like you're going to train that MLlib model and you're like, all right, I have a random forest regressor model object that comes out of my training. I just did a fit on it. And this is the return type object. There's probably not going to be an API or a method that's going to be added to that that's going to say, hey, generate my explainability and generate my cross-validation reports and do all the statistical validations of everything. That's probably not in the cards, but other APIs are being built internally at Databricks to supplement a lot of that stuff, to give not just the report that you get from like a dot summary, but much more comprehensive model explainability. It's like, hey, I've detected that this is a multi-class classifier. Here's your confusion matrix. I'm going to pre-generate that for you. So from the Databricks side, with Spark ML, we don't do that in Spark ML. We're trying to minimize the amount of code that gets added to Spark. It's already big enough as it is. So instead, we put that functionality in MLflow. And as of this last major release of MLflow in 1.25.1, we have model explainability, where you can take a PySpark model from MLlib, you can take a Spark data frame that you use to train it or your validation data set and just say, hey, explain this for me. It'll detect the model type. It'll generate all of your charts for you. Instead of putting them into a notebook output, it just logs them all as artifacts into MLflow. So when you go and look at that model that's been put into tracking, when you go into the artifact viewer, you can just see all of those charts. You're like, oh, cool. That's my area under ROC, and that's my area under PR curve, and there's my confusion matrix.
What's the rationale for like sklearn's one-stop shop versus Spark's assemble several packages to get the end result? Is there a design behind that, or is it just coincidence?
I think with sklearn, because it's predominantly a pure open source setup that's contributed to from volunteers from all around the world, they have a guiding principle of pure open source for that, where it's like, hey, we can dump whatever we want. There's a controlling council on the committers for sklearn, and they vote on, hey, what do we want to include in this API? What do we not want to? How do we want to standardize stuff? What are our guiding principles here? And they've chosen to attempt to make the modeling aspect of building a model self-contained within that API. Once you deviate from what is supported, you're going to have to use different packages. You're going to have to think about infrastructure a little bit more about where is this going to run? How is it going to run? What do I have to do to my data to get it to work with these different APIs? It can get a little bit more complex. From the Spark side, we have a temporal issue that's going on. So we have Apache Spark that was built a decade ago, and MLlib was part of the first public release of Spark, had MLlib in it, the RDD API. And over time, it's grown and it's matured. to the point where the APIs are very consistent among themselves. There's still a couple of areas where it's like, that could be better. But generally, it's a very fluent and approachable API. And we didn't want to take something like MLflow and put it into Spark. It just doesn't make sense to do that. So MLflow is built as its own project. And it's built in an agnostic way where it's not Spark-centric. It's not sklearn-centric. It's just a framework that you can build whatever flavor you want, and it provides the templates for functionality. Like, hey, this is how we need to think about this. And most of the people that are contributing these major contributions to MLflow of these new APIs, they're all Databricks employees. For stuff like explainability, I worked with the guy that built that whole thing. It was just, he designed it, he built it, we reviewed it, he fixed some stuff with it, and we released it. But the principle of how that was built was, we're not taking sides on any packages that people are doing. We're just looking at, hey, we can support these two different data types, or actually I think there's like 5 data types for that API, but we're going to take in basically a Pandas data frame or a Spark data frame. We don't care what model you're pushing to this. We don't care where you even trained it. We have no skin in the game there. We're just building this to make it so that it works for people and so that it's useful. And you take that model, you pass it to the data. We're going to figure out what basically the transform method is. Like, how do I get a prediction out of this from whatever model you pass in? We're going to do some inspection of it. And then we're going to generate predictions and run that through. We're actually using sclearn library for doing the validation checks on that instead of using Spark, because we don't need to. We can take a sample of the predictions, and that sample summary data we can use to generate the curves and plots and any metrics that we need to auto-generate.
Got it. So if you do have to assemble different packages and different tools to have an effective Spark ML implementation, what is the minimum number of packages or the minimum package set that is required to, let's say, do some EDA? Probably not build a proof. Let's say we're building a proof of concept for your team to review to say, hey, let's now productionize this. What's the minimum package set that you usually use?
Ooh, that's a good one. For supervised learning, traditional ML, if I'm doing EDA, most of the tools that I would need to do stuff like feature culling and analysis of quality of features, I can do natively in Spark. So there is a Spark ML sort of explainability. It's kind of like an EDA toolkit that exists in Spark ML. And I can do stuff like pairwise comparisons, and I can get COV. I can measure that across different features. And I can say, give me the Pearson's correlation coefficient between these and tell me, are these positively or negatively correlated? And then I can plot them, and I can fit simple regressors to them and determine, what is this relationship? Is this going to burn me if I include both of these? Or should I, combine them in some way? Or should I drop one that has less of a fit effectively to my label? So you can go through and do all that natively in Spark. If you have more advanced like interactions, like pairwise interactions that go beyond a second degree order, you're probably going to want to use stuff from sklearn. And that can get a little tricky because you're going to have to subsample. You can't call an sklearn algorithm from a distributed Spark data frame. You can do a pandas apply, but that's going to operate on partitions that exist on workers. What some people do is they downsample the data and then run it locally on the driver after they do a collect. That can get a little dangerous. You can out the driver and all of a sudden Spark crashes. So it really depends. But then for the other parts of production, when we're talking about model training or model selection, all of that stuff can be done, whether you're doing, if you're doing it native PySpark or stuff that I've done in the past, Scala, like native Scala Spark with the data frame API or the RDD API, you can build most of it with the pipeline API in MLlib or in Spark ML. And that'll get you all the way to the point of getting a prediction out of something, like feeding in a raw data frame. It'll do whatever filtering it needs to do. It'll convert types to, because that's the other thing to remember. Spark is a strongly typed language. So it needs to know exactly what the types are of everything, and it keeps track of all of that. The pipeline API wrapping that around all of these different modules that you're using in Spark helps keep your code clean and very efficient. But you can generate a pipeline that has, a wrapper of Optuna or HyperOpt around your actual model tuning to the point where it'll select whatever the optimal hyperparameters are for that pipeline. And yeah, that's pretty much as far as the model generation goes. That's where it ends. When we go into validation and explainability, you can throw a pipeline through the ML flow explainability, and it'll generate SHAP reports for you, and it'll tell you, like, hey, this is our best attempt at model explainability through the supervised learning algorithm. But for a deployment aspect, because of Spark ML's designed for extremely large data sets, usually you're using that on batch, where you have some enormous amount of data that you need to make predictions on every day or every couple of hours. And that ETL process that's populating that, you're like, all right, every day we need to predict what's going to happen or what the probability of this thing happening or something, whatever that use case happens to be. Usually doing like a cron schedule for a job. You're saying, all right, at 2 a.m., we're going to predict for the next day. Or hey, every 2 hours on the hour, we're running prediction on whatever we haven't predicted since. So you set up a structured streaming trigger once pipeline. It's like an ETL pipeline. And you just load your models, your Spark ML pipeline through that. And you say, hey, .transform on this structured streaming data set. And you're going to get a ton of predictions that come out of it. They're going to come really fast because it's distributed. That Spark ML pipeline is pushed to all the workers when you actually load it from object store or load it from disk. And if you want it to go faster, or if you want scalability to be less of a concern, you just start more workers. And it generates those predictions. You write them out somewhere, and that's your production pipeline execution for what most people use Spark for. There are other use cases where you can do semi-real-time prediction, which is the same sort of setup. Structured streaming, and we use structured streaming because we maintain state. So you're not going to have to deal with, I need files that were written to disk from 59 minutes ago until right now, and then I'm gonna write out what the now timestamp is to somewhere. Please don't do that if you're thinking of doing that. That's really dumb. Just use structured streaming. It maintains a file history of what has been touched and what has not been touched. If you want it to perform like batch, you just say trigger once. And within that trigger once execution, you can convert from a streaming data frame to a native Spark data frame. So you can do whatever Spark operations you want within a streaming context without it interacting with the streaming data frame. That being said, the semi-real time is you turn on that structured streaming, and instead of trigger once, you just say trigger continuous. And that limits your options. You can run a Spark ML pipeline through that just fine. What you can't do is stateful operations without having to modify the code, and that'll increase complexity quite a bit. So you can do a trigger with a for each batch where you say, hey, I want to trigger execution every 5 minutes, and within that 5 minute, whatever data came in, that's going to be acted on like a Spark data frame. And then you can do whatever logic you want, as well as running it through your pipeline. But there's that continuous mode operation, you can't do that. There is no state. It's just checkpoints that are like, hey, I read, up to 30 seconds ago, all the files have been processed. I'm going to read 30 seconds ago till now. I'm going to take all of that data and stream it through a Spark ML pipeline. I'm just going to get predictions that come out. I need to write that stream out somewhere. So you would do something like read from Kafka, apply your basic feature transformation into that Spark ML pipeline, and then you'd write back out to Kafka. And that would be a semi-real time. There's latency associated with that most people who are doing real-time serving are not really happy with, because it's the JVM. Like there's a little bit of overhead there. You're not going to get 15 millisecond latency while predicting 100,000 records a minute. It's just not going to happen. You're going to have 400 millisecond latency because there's some serialization, deserialization that's happening there. Encoding, validation, type checking. There's things that the CPU has to do. The other option is for serving it through like a REST API where you don't want to start up Spark to do something. You just want to have like ad hoc on demand. You can send something to a REST API, but still use a Spark ML model. And you would have to serialize the model as an MLlib model. MLlib is a infrastructure framework for Apache Spark where it'll spin up the bare minimum packages that a JVM would require in order to execute Spark instruction sets. You can't do anything on that like VM that's running that. It's not like you have a Spark context that you can interact with. It just doesn't work. But it allows that model or that artifact to be exposed in the JVM as something that can process data that's coming in, and then it'll run it through the algorithm that's in there and then spit out predictions or whatever the output of the pipeline is. Your mileage may vary with that. It's not as simple as I'm making it sound. There's some considerations that you need to do in order to get that working. You also need to build your own hosting infrastructure for that, which that can get fairly complex when you're dealing with MLlib. But once you get it working, you can get some pretty good latency with it and ludicrous levels of throughput.
Got it.
Hi, this is Charles Max Wood from Top End Devs. And lately I've been coaching some people on starting some podcasts and in some cases just taking their career to the next level. You know, whether you're beginner going to intermediate going to advanced, whether you're trying to get noticed in the community or go freelance, I've been helping these folks figure out how to get in front of people, how to build relationships, and how to build their careers and max out and just go to the next level. So if you're interested in talking to me and having me help you go to the next level, go to topenddevs.com/coaching. I will give you a 1-hour free session where we can figure out what you're trying to do, where you're trying to go, and figure out what the next steps are. And then from there, we can figure out how to get you to the place you want to go. So once again, that's topenddevs.com/coaching.
Yeah, so that's definitely probably a step 2 or a step 3 after building that initial model. But you hinted at one thing that I very strongly believe in, which is downsampling your data so that you can iterate quickly and work with more usable libraries. I've noticed that whenever I'm working with very large data sets, even if it takes 10 minutes to train or 20 minutes to train, if it's giant, that's fine. You downsample, it takes 10 minutes to train. That's the best you can do. But if you can decrease training time and results time, I would argue that's one of the most valuable things you can do as a modeler, whether it's ML, inferential, you name it, because you can get that feedback loop a lot faster, get results a lot faster, and you're essentially spending less time just sitting there responding to emails or responding to Slack or whatever you do while models train, doing push-ups, which is highly recommend. But that's one point. And then another point is that whatever plotting library you use, I'm a big fan of Plotly for Python. Whatever plotting library you use, they often take a very long time to run if they have large data sets. So downsampling it not only increases your iteration time, but it increases the amount of things that you can do, the amount of libraries that you can use. So it's good to hear that even in the Spark world, downsampling is a useful tactic.
I mean, we have to. When you talk about production grade hyperparameter tuning for models, typically when I do that and I'm trying to figure out like, hey, where should my search space even be in order to fully optimize this thing? I'm not going to take, if I'm looking at a training data set, all the data that I have available, it's like, oh, it's 14 terabytes. I'm not going to build a model on that, at least not when I'm tuning it, like from the scratch. We're no longer talking about a 10 or 15 minute training time. We're talking about a 60-hour training time on something like that. It's just massive.
Here's a super anxious question, though. What if we're missing something? What if we're throwing out useful information that was in those other 55 terabytes or whatever of data? Then
we are. I mean, when you get down to it, any model for machine learning is throwing away innumerable amounts of information. It's the hubris of the ML practitioner who believes that we can capture reality with data. It's just not possible. So even if you're collecting everything that you can think of, everything that you think is measurable about a particular problem that you're trying to solve, and you're like, all right, sweet, we have 850,000 columns worth of data. that we think really explains this problem. You're probably less than 0.00001% collecting the actual data that would fully explain the nature of what's going on. So even from the get-go, we're blind to the problem for the most part. But we also have this assumption, or at least a lot of people in the data science community do, of like, well, I need my model to be as accurate as possible. And I need all these edge cases to be as, part of this model. So the model can learn these things. And I would argue, and I do argue with people about that, saying you actually don't want that. What you want is generalization. You want your model to generally be right most of the time, or at least as close to the approximation of what we classify as rightness or correctness as much as possible. No model is ever going to be right all the time. If it was, nobody would have to retrain models. It would just adapt to the data dynamically because we collect all the information and it's been trained on all the information. Then it should know, right? It should just be adapted to that. That's not how any of this stuff works. So we want generalization as much as possible. So downsampling, you're throwing away extreme outliers. Depending on the algorithm that you're using, you're already doing that anyway. If you're using regularization in a linear model, it's already culling that stuff out. If you're using a tree-based approach, it's already ignoring all that stuff, unless you've told it to specifically adapt to that level of outlier by saying, hey, I want my max depth to be 500 and my leaf size can be 1. Then that model is going to learn. It's definitely going to learn all of those outliers, but you've just overfit the model like crazy. And you've just created a model that is truly massive. Like, good luck serializing, like saving that to disk. I don't know if you've ever seen like a random forest model that's been trained or tuned in a really odd way. You're like, hey, maximum number of trees, 50,000, and I want 10,000 iterations of training. I want a max depth of 100 and minimum sample size split 2. And then you look at the size of that model saved on disk. And you're like, how is that even possible? This is 8 gigabytes. Like, what the hell is going on here? But that's why, because it built a tree that's that big, or an ensemble of trees that has 400,000 nodes in it.
Yeah, to be perfectly clear, you can fit a decision tree to every single data point and get 100% accuracy every time. That's always possible.
Yep.
It's just a rule. Like, if data point is number 55,312, well, then the number is 6. And that is not what machine learning is. That's optimizing accuracy. That's not building for generalizability, as Ben said. But I have a question. So you said downsampling is really effective for a variety of reasons. What % of the time do you train and optimize on downsampled data? And then when you sort of ramp it up to the big full data set, do you see trends reverse or coefficients change or discover new things that are actually very valuable features that weren't fit during the training process?
More frequently than I would probably like to admit. That's usually on problems that, like, I'll see stuff like that on problems that I'm working on that I don't fully understand the problem space that I'm working in, which is a hampering of most consultants that are out there, where you're like, oh yeah, I'll give you advice and I'll show you some stuff. Let me get a sample of the data, or hey, thanks for access to your data set. I'll try some things and show you what the differences are. And I'll do an initial training round on like maybe 5% of the data, because I just want an answer fast, because I'm on the clock and I've got stuff to do. And I want to be able to talk to the customer the next week. So I know that in 5 working days before my next conversation with them, I need to do 10 days of work in 5 days. So I'm rushing through stuff and I'm not doing full EDA. I'm not validating everything like I would if I was working on the problem as an owner of that problem. So things get rushed. I don't fully, understand the data. I haven't had a chance to talk to any subject matter experts at the company who own that data. And I don't mean talking to the data science team. I mean talking to that person from marketing or that person from ops or whoever really understands this problem. So I don't have context. So I'll look at the results and I'm like, oh, that looks okay. I'll stick with that range of hyperparameters because I ran 100 iterations on this very wide range. It seems like everything's kind of within this band. Look at, as you said, like I'm doing a linear model, look at the coefficients, be like, yeah, it kind of seems right. Or it seems like it's not crazy. And then do some simulation and I'll run, samples of validation through that linear model and look at the results and be like, yeah, that seems like it's legit. And then 2 days before that discussion with them to show them what the actual result is, I'll run it on all the training data. And then sometimes you're like, wait a minute, I didn't think feature number 14 was going to do that. Why is that changing this so much? And then I go back retroactively, look at it and be like, oh, there's a negative correlation here between these that I wasn't paying attention to. And I need to drop that column because it's messing this up. So ML is an iterative process. I've met people who have claimed that they know how things are going to go. They're like, well, this is the model that you use for this use case, and this is why, and I can derive it for you on a whiteboard. Like, great, man. But everybody that I've known that's done, like, actually push stuff to production to solve problems, they've all had the same sort of take that I've had with stuff like this, where it's like, yeah, we think we know what's going to happen. We have some educated hypotheses, but we're going to take the scientific approach and we're going to test them out, validate, check to see what our results are. Did our hunch pay off? And sometimes it doesn't. You got to go back and change it, fix it.
Yeah, that's a great point. Yeah, there's not really an alternative, unfortunately, unless you have unlimited time, which is pretty rare. If you really want to be a stickler, an option is so the whole point of downsampling is to iterate quickly. And if you want to ensure that your sample is representative of the population, or at least the data set that you have, you can check if the distributions are roughly matching that of the entire data set. If you want to get really fancy, you can do tests. Tests are usually overkill, but just eyeballing a histogram of your sample and your population data is usually pretty effective. And again, if you need a p-value, feel free, but that's usually overkill. Cool. Any other points in this area, Ben?
I mean, I think it would be remiss to not mention the fact that, like, yeah, we've been talking about Spark MLlib sort of versus sklearn and stats models and PyMC3 and all these other algorithms that are out there, these libraries. But I'd say that for the last seven years that I've been using Spark ML and Spark as a platform in general, my ratio of using MLlib versus any other open source library is probably 20% to 80%. So I use sklearn way more than I use Spark MLlib, like way more. Stats models too, particularly if I'm doing stuff like anything where I can get away with a very simple regression. That's my bread and butter. I love that stuff. If I don't have to actually, Spark ML doesn't per se, but Spark as an execution platform does. So we have Pandas UDFs where we can take an incredibly large data set that's loaded into Spark, and we can chunk that up. I mean, it already is chunked up on all the different workers. We can apply single node Python code onto each of those distributed workers to operate on either its subset of its data that it has on that worker, or we can shuffle data around and intelligently co-group stuff together so that we can just use a bunch of machines in parallel. So we can get away with hyperparameter tuning that actually horizontally scales. You have to do some funky stuff with hyperopts, and you have to, there's no free lunch. So you're going to be hampering the Bayesian optimization algorithm of that because you're doing it in a distributed way. But if you set your search space just right and you do enough iterations, you can specify and hey, on a single machine, I might have been able to get away with 100 iterations with hyperopt. Well, on Spark, you can say, well, I have 20 worker nodes and I can do 20 iterations at a time before the next Bayesian optimization that happens. And the Parson estimator can look at what the priors are and adjust a new search space criterion. But with distributed hyperopt, you can say, hey, do 20 of these in parallel, and I'm going to iterate over that 50 times. So you can test way more stuff because you're just doing it in parallel on different machines. So I use stuff like that with pretty much any project, unless it's a recommendation engine or I know that the inference data set is so big that it just makes it simpler to use Spark MLlib, which there's plenty of use cases in industry like that where you'd be shocked at the volume of data that people need for running predictions. talking about like fraud detection algorithms at massive scale. You're like, whoa, how many transactions do you need to run? You're like, well, it's 1.8 billion a day. Wow. And you just need that batch. Yeah, we're not acting on it. We have a different algorithm that does the real-time stuff. This is to see how well that one's doing and see if we catch any other, missed things retroactively. Like, wow, that's a big job. And they're like, yeah, but on Spark, this job executes in like 6 minutes. Cool. Right tool for the job sort of thing.
Yeah, it's crazy what parallelizing can do. Never ceases to amaze. Cool. So I think final topic, do you have any good resources, any tips for people either coming from native Python, like sklearn type libraries, into Spark? Things to do, things to not do, and good books / articles?
I mean, the first step that I did when I was learning these APIs, I came from a background of understanding. I was using SAS before I was using Python and sklearn. So I already had that like statistics background of a practitioner. Like, oh, these are the the tools and functionality that I need to do this particular modeling task. And this is what I know how to do in SAS for validation of my hypotheses. So I went from that directly into Spark, basically, and like Spark ML for the first couple of projects that I did coming out of, traditional industry. And I went with looking at the demos actually in Spark ML docs and looking at the examples. And I actually just copy that notebook into a Databricks notebook and just start breaking it. I'm like, well, yeah, I see the example here, but I know that in SAS I would do this sort of thing with data. So can I actually do that? And I'd end up having 30 tabs open with 30 copies of notebooks from the Getting Started guide from Apache Spark. And I'd just be copying and pasting different pieces together and seeing what you can and can't do with the API. And after a couple of weeks of, playing around with that, I started to get a little frustrated and I was like, how does this thing even work? Like, I don't understand why this API can't talk to this other one. Like, why can the output of this can't go into this? What's the difference between an estimator and a transformer? Like, this doesn't make any sense. Luckily, Spark is open source. So I just went into the GitHub account of open source Spark. And this is before I worked at Databricks. So that was my only access to source code for anything on Spark. And I just started reading through MLlib's implementations of the RDD API and instantly got confused and overwhelmed. I was like, this is like ancient Greek to me. I can't read this type of Scala code. And what is Breeze? Like, what the heck? I just started Googling stuff and I started to find a bunch of sort of blog posts, and there's some guides out there. Jacek Laskowski, he's a contributor to open source Spark, and he's a very prolific writer online. If you want to know anything about Apache Spark, he's probably written something about it, and his books are also great resources. But I started to read through that, like the design criteria of how these things worked, and it started to click a little bit more. And then I'd look back in the source code and be like, oh, that's why that's written that way. And oh, that's how an RDD is done in this way. And okay, that makes sense. And then when Spark ML came out, the data frame API, because I already known kind of how the RDD API worked, data frame API was just like, wow, this is glorious. Somebody put a wrapper over this super complex stuff and made this so simple to use. And it's just been improved on over the years to the point where you can build a full end-to-end Spark ML implementation if you don't have to do any crazy sort of custom logic and transformations because your data is kind of funky. But if you have columnar data and you've already done your feature engineering work, you can implement a pipeline in less than 60 lines of code in PySpark. It's pretty efficient. But that's kind of how I got started learning that stuff. And then throughout that entire period was just playing around with as many open source data sets as I could get my hands on. The UCI data science repository is free to use. I recommend any ML practitioner download all the data sets. Some of them are broken, fair warning, or require extensive cleanup. But there's a lot. It's like a gold mine of ML data sets that are there for lots and lots of different use cases. A fun tactic that I've used with people who express their desire to want to learn ML. They're like, "Oh, teach me what you know." I'm like, "Sure. Here's the fundamentals. We'll have some, couple hour long conversations, and I'll talk you through what this is and what it isn't, and separate the reality from the hype." And then usually people are like, "All right, can you give me a project to work on?" And I'd say, "Sure. I want you to download all these data sets, and I want you to go through each of them in a spreadsheet and tell me what type of algorithm would be used to interact with this." And just to see how much they grokked from like our initial discussions. Most people don't get it correct, but it's a good test for people to go through. And the test is look at the data set and try to come up with a use case based on the data that you're looking at, and then build a model and see if you can build a model that's not total garbage. And you try to do that in a platform or an environment that you never used before. And that's a great way to learn MLlib. Or if you're coming from MLlib and you're learning stats models, that's how I learned stats model stuff, not just for the forecasting APIs, but for the more traditional statistical aspect in stats models. We're like, hey, I need to fit a polynomial to this data set, and I need to learn these APIs. Well, I'm going to go back to my old trusty data set, UCI ML library, and I'm just going to pick a random data set from here, and because it's all real data, it's not synthetic stuff, and see if I can fit a polynomial, like a fifth order polynomial between these two vectors.
Hey folks, if you love this podcast and would like to support the show, or if you wish you could listen without the sponsorship messages, then you're in luck. We're setting up new premium podcast feeds where you can get all of the episodes released after Christmas 2020 without the ads. Signing up will help us pay for editing and production, and you can go sign up at devchat.tv/premium.
I absolutely love that idea, because I think a very underrated job in modeling in general is picking the correct algorithm or model for the given data set. You can usually get, if you can think linearly and have some intuition about data, you can usually optimize models pretty effectively. But having a good starting place and starting point can just speed up development millions of times.
Yep.
That's a really great idea. Cool. Yeah. I'll take the other end. I usually do what Ben does, which is get into start from zero, get into some data set, try to make something work. When it doesn't work, get mad, look at docs, get confused, iterate. That's my usual approach. One alternative approach that I've also used is essentially reading an entire textbook at a high level, getting a lay of the land, knowing what's there, what maybe isn't there, then going in. If you know basically if there's a feature built into a library that will save you tons of time, that will solve your exact problem, it's sometimes hard to find in the moment. But if you have a general understanding of what's out there, it's a lot easier to go and think back and say, hey, does this exist? If it does, Google these specific keywords. And then start building out your specific skill set. But I think it really depends on the type of person. If you need immediate feedback and immediate rewards of, oh, hey, this is a graph of my predictions, then usually it's best to just go in and get dirty. If you're trying to master a subject, I would argue that doing the textbook approach, then getting dirty, is probably more efficient.
I couldn't agree more. And also, with people's expectation that mastery is attainable in this field in a short period of time, it's going to be a disappointing experience for people. They're like, hey, I went to get my master's in data science because it's a new degree at the university, and assuming that 6 months after they get out of that program and start working at a job, that they're going to just intuitively know how to solve all ML problems. It's not going to happen. It takes years of creative, frustrating mess ups, I guess is a political way to say it. Years of just falling on your face and then figuring out how you messed up and how to make something work better before you're going to get to the point of mastery of the practitioner aspect of it. I think you can master the theory of it from reading a lot of books and take your approach. I think if you really want to learn a subject, read about it and then write about it. And you're going to learn a ton about that topic But then the applied aspect of that it comes through just repetition and doing the work over and over and over again before you start to memorize those patterns in your head of like, okay, I know this won't work. I need to try these other things. And this is the most efficient way for me to go through and figure out how to exactly like what you said earlier with looking through a library and using something that's pre-built instead of rolling something yourself is a very underrated skill. And I wish more practitioners would go and do that. Sometimes I wish people would just read the API docs of a library, because a lot of the times it's in there and it shows you like what has been built. It just saves you so much time. If you're like, hey, somebody already thought of this. It's not a hit against you that you're using somebody else's code. Like, that's why they gave it to the world for free. Like, use it.
Agreed completely. And sometimes like writing stuff from scratch is faster. Like, I don't use RMSEs. Usually I just write the one line of Python that's needed to calculate it. But if it's a more complex function, or basically knowing what tools are out there and then making an educated decision is super valuable. And Ben's 100% right. Usually there's pretty good stuff out there that not a lot of people know about because it involves the boring and non-sexy work of reading docs.
Mm-hmm. All right. I think we covered everything we wanted to from where we left off last time. So I guess this pseudo closes the chapter on talking about Spark MLlib for now. Maybe we'll bring it up again later on. But yeah, this has been fun. Hopefully informative for listeners. A little bit of insight into how we learned these libraries and how we continue to learn new things. And hopefully we'll give people some insight into how to optimize that process for themselves. Because that's really what this profession is. It's continuous learning on steroids. There's always something new. There's always something that you can apply. People are always building new things that you have to learn, or you should learn because they're interesting and they can save you a lot of time and effort. So yeah, hopefully this was helpful for people.
It's helpful for me.
All right. So until next time, I've been Ben Wilson.
And Michael Burke.
And we will catch you all in the next episode. Take it easy.
Thanks, everyone.
Bandwidth for this segment is provided by CacheFly, the world's fastest CDN. Deliver your content fast with CacheFly. Visit CacheFly.com to learn more.